Today is July 29th, 2021. My name is Matt Willard, and I'm a professor of material science and engineering at Case Western Reserve University. Today is my honor to interview Dr. Robert D. Shull, Fellow Emeritus from the National Institute of Standards and Technology and former president of TMS. Bob, we've known each other for a long time, both through technical committees and through outreach, especially Adventures in Science. These are great interactions where we've had lots of conversations, but we don't usually get a chance to talk about you and how you became the well-known scientist that you are today. So I think we should begin this interview with a discussion of where you come from. You grew up in the years just after World War II. Can you describe, kind of your early life and what kind of inspired you to become a scientist?
So I was born in 1946 in Oak Ridge, Tennessee. My father was a scientist at what would in the future become the Oak Ridge National Laboratory. At that time, it was called the Clinton Pile. They had developed, of course, this wonderful source of neutrons during the war there, and then my father joined that laboratory just after the war, not too long before I was born. And so I grew up there for the first 10 years of my life, and it was a wonderful place to do that because it was right next to the Smoky Mountains, and my father was quite interested with my mother to take myself and my two brothers. So I'm the middle child of three boys, and we would go up camping in the mountains and hiking and enjoying water sports at the local lakes, which had been created by damming up the Tennessee River. And but when I was about 10, we moved up to New York State for about 2 years. We lived out on Long Island in a city called East Patchogue, while my father worked at Brookhaven National Lab while they were building a nuclear reactor up at MIT. And my father did not want to spend the 2 years it was going to take to build this reactor that he would work in doing nothing. So he took a position at Brookhaven Lab and worked there for a couple of years, and then we moved up to the outside the Boston area, where my father became a professor at MIT. And so at that point, I was in near the end of elementary school, but I did spend a couple of years there. My life was a reasonably comfortable life. We did a lot of hiking while up in that area, up in the White Mountains of New Hampshire and Vermont. And I can remember, in fact, building a sailboat at a house that my parents rented during a couple of weeks in the summertime every now and then. It was right next to a lake, and that was a very enjoyable experience because it was a rectangular boat rather than designed like a normal boat with a nice pointed bow and stern. And in fact, I went online in those days, not online, but in the newspaper. The New York Times had this big advertisement section, and I remember buying a parachute. And then my mother and I spent many hours ripping out the cording from that parachute. And then my mother did some sewing to kind of take out the billowing parts of the sheet. And we used that for making the sail of this sailboat. And I think
how big was this boat, Bob?
Before it sunk.
How big was the boat?
The boat was about I guess, maybe 12 feet long, something like that. So it was not a real long boat. It was about maybe 3 feet wide, something like that. It had a gaff rig on the sail, and so it was fairly light. It was kind of a platform boat, so if it turned over, you did not get much water inside, and thereby you could right it while you're in the middle of the water.
Did you do this with your siblings?
Actually, this particular project I did pretty much by myself and my father. When he was up there, he would kind of commute from MIT or his laboratory at MIT and up to this cottage. We would be up there for about 3 weeks, I think, 4 weeks, and he would come up on weekends. And that's when he would be working with me, and at the other time I was doing it myself. But
so engineering from an early age.
Exactly. So that's where I really got my start. Actually, I got my start when we were in Long Island, and my two brothers and I decided we were going to build a log raft, and we were going to sail it out to Fire Island. And we lashed all these logs together and put a mast on it and a square rig sail on it, and we got about 15 feet from shore, and it kind of tipped over on us. And the worst part of that was not the drowning; it was the fact that that whole area is infested with horseshoe crabs. Oh. And so there are all these horseshoe crabs running around the place while we're trying to get out of the water back up to the beach. So that was a real failure, but it didn't stop me from trying to build a regular sailboat much later on.
So what about getting a little bit older, going to high school? What were your interests?
So my interests were mathematics and the sciences. At my high school, they were the offerings were typically chemistry and physics. I don't even remember biology being an offered science courses. And I liked them. I was good in them, and I figured later on I would probably end up majoring in one of those areas and working in that area. It was pretty much accepted, I think, not expected, but accepted by myself and my two brothers that after high school we would go off to college. Obviously, my father had gotten degrees in college, getting a PhD degree. And my mother also was somewhat unusual for her time, that she also went off to college, but specifically went to graduate school. In fact, that's when my mother and father met, was when both of them were in graduate school in New York City. My mother at Columbia University majoring in history, and my father majoring in physics. And so I always had the expectation that after high school I would go off to college. It was not a question in our mind that we would do this. And in fact, I did that as my two brothers also did. But things I liked doing when I was growing up were playing with this train set and helping my father helping me and my two brothers build this very elaborate train set comprised of two big intersecting at right angle 4x8 sheets of plywood that were at different levels, and we built a paper mache mountain at the intersection, and we would have trains going up from one level to the other and down, and built villages with lighting and everything. And the thing that I guess I particularly enjoyed was working with my father, wiring up all these electronic controls for turning on lights, or having a gate come up that stopped cars from crossing the railroad tracks, or uncoupling cars. I mean, that was really a lot of fun, and so I enjoyed doing that, and tinkering around with kind of electronic things. I never built a radio or anything like that, until much later on, and I got one of these Heath kits. In fact, I'm not even certain they still exist. Heath was the company, and they had kits where you could build amplifiers and radios and things. And so I built this big amplifier. Took hours and hours, but really it taught me a lot about soldering, for instance, how to make good solders. That's something, unfortunately, that's missing in today's training of our youth. The children generally don't get a chance to experience and learn that sort of technique. That's, and I was also quite active at running. I was very good at running long distances. In fact, I remember this one year, this Boston Marathon runner called B.B. Bikila came to our high school to run with us during practice. He was from Ethiopia, and he was going to run the Boston Marathon. We lived in Lexington, and which is only 10 miles from Boston. And so Bikila came out to run with us, and his pace was faster than my sprint, which made me realize how slow I was, of course, but I enjoyed it. And this particular marathon runner was well known for winning the Boston Marathon that year, running without shoes. So he ran it barefoot, and quite an impressive individual.
So you had a lot of different types of activities. This is creative things that you were doing, kind of unscripted, and then team sports types of things. I think that shows something about your future career, where you are, working in teams and being very creative in your work. So you get through your high school career, and how did you decide what, you said that it was kind of expected that you'd go to college.
Right.
How did you decide where to go, what to do next?
Well, I actually, I applied to maybe 4 different colleges, and they were all reasonably competitive colleges. And I remember going to this one interview for Dartmouth, as I recall, and most of the colleges required an in-person interview as part of the application process in those days. And I remember going to the interview, and the interviewer looking at this list of colleges that I had applied to, and he says, "I don't see a safe school here." And I was considering Dartmouth as a safe school. That got me a little concerned. Well, I didn't need to be concerned, because I got pretty much all the ones I applied to. And I was all set to go to Cornell. In fact, I decided that that's where I was going to go. When my parents said, well, if you went to MIT, then you could live on site. My original thought was that I would be living at home and commuting, and I really didn't want to do that, because I wanted to get away from parents, of course, like most children at the end of their high school years. And when they indicated that I would be able to live on the campus, then I decided that that's where I would go. And but when I went there, like I said earlier, I was planning on majoring in either mathematics or chemistry or physics, because those are topics I was good at and I enjoyed them. And I wanted to learn more about those topical areas. But I quickly found out that mathematics really didn't suit me, because it was much, much too abstract. Physics also seemed to be a little abstract, in the sense that the sorts of laboratory experiences I had in high school in that area, which I'd like, but they were all kind of can type laboratories, and I wanted something that had more connection to real things. And so physics didn't suit me as well as at least I liked. Chemistry, I also quickly decided I could not major in or work in the area because I couldn't pronounce all the names of all these chemical compounds and or remember their names. And I also couldn't keep straight which is positive and negative, the anode or the cathode. So I couldn't see myself in that area either, which left me with a quandary. What am I going to major in? And I think something perhaps was a little stupid at the time because I didn't know any better. In hindsight, actually, it was a very foresighted method I chose. I looked at the departments at MIT, which required the fewest number of required courses in that discipline, because I really wanted to still take courses in math and physics and chemistry because I still liked it and I wanted to learn a little bit more in those areas. So if the particular discipline I chose to major in had the fewer required courses in its own discipline, that meant I was free to take courses outside their department. And the particular discipline was material science at MIT that had the fewest number of required courses in it. So I figured this is the course for me. And so I subsequently began taking courses in material science, and as well as...
Was it called that at the time, Bob?
In fact, MIT was called the Department of Material Science. It was one of the big first universities to do that. Most other places were metallurgy or mining and metallurgy or chemistry departments. Now, most all material science departments are material science departments. But at that time, MIT was quite ahead of others in that regard. And so, as I say, in hindsight, it really was the best thing for me because material science includes elements of all three of those disciplines, plus biology and other activities. And so that was really the right place for me.
So at the time, your father was still a physics professor at MIT.
Correct.
What types of interactions did you have with him when you were an undergraduate? Did you take any of his courses or I don't know?
No, I never took a course from him. I was a little scared, I think. I joined a fraternity called Phi Sigma Kappa when I was a freshman at MIT, which was really a good thing to do. And in fact, the fraternity system at MIT is a wonderful system. It's quite different than the fraternity systems at other universities, I think, in the sense that all these individuals, brothers, are working to help others. And at MIT, being a very competitive place, you really need to work together, get assistance by others, and it's a very good atmosphere. At any rate, there was when some of the brothers knew that my father was Cliff Shull, professor at MIT, they took delight in letting me know that the nickname that the students had for him was Flunk-em-all Shull. So as a consequence, I wanted to make certain I did not take a course from him. But I would see him on occasion, and it was useful for him to be there and have a car I could borrow on occasion. So that was handy. And I did go to listen to one of his lectures he was giving to the physics department once. And unfortunately, had spent the whole night staying awake working on a humanities paper that was due that particular next day. And when I went to listen to this lecture of my father to the physics department, and my father made a mistake as far as I was concerned, that he would turn off the lights and show some slides to the people during the talk. Then he'd turn the lights back on and talk a little bit more, and then turn the lights off again. I made it through the first time he turned the lights off. I did not make it through the second time he turned off the lights. And so the next thing I knew, people were clapping, and people started to file out. So I did the same thing. I didn't go up to see my father at that point, but I saw him the next day. Sometimes in order to get a candy bar from his bottom right drawer of his desk, which I found out quickly is where he hid them. And he said, I hope you don't learn in all your classes through the osmosis of your snoring. And so this was the way he kind of handled it, I think, at the time.
So he did notice.
So he did notice, exactly. My suspicion is that most everybody in the lecture noticed too.
Okay.
While I was at MIT, I didn't do really well scholastically my first semester there, and so as a consequence, I did have to take the physics course again of that first semester, and so I did that during the summertime at my freshman, after the end of my freshman year, and it turned out to have been a very fortunate thing that I was doing that, because that's when I met my future wife. Since I was on campus taking this remedial course, I found out about all these different dancers, or mixers, they used to call them, at different places around MIT, and where you could meet other people, male and female, and my future wife, Mary Carty, happened to attend one of these mixers that I was at, and we got to dancing, and then we would meet up after that on occasion on dates to go to the beach or see a movie or something, and we subsequently got married at the end of my senior year at MIT.
Fantastic.
So it turned out to be a very fortunate thing that I was not so good scholastically that first semester. Luckily, I did much better after that first semester. I think that in fact, this is something I tell students all the time when I'm interviewing them for college, which I've done for many years here locally, and that is, and I was pretty good in high school in the sciences and mathematics, and I kind of thought when I got, so I didn't actually have to do a whole lot of work doing the homework, and I kind of thought going to college would be the same thing, that I wouldn't have to work so hard in these disciplines. Well, it was a rude awakening for me that first semester to find that everybody else there was equally good, in fact a lot better than me, and I had to do some work. But it took me several weeks to find this out, and by that time, I was in a deep hole because I wasn't doing, if I couldn't do a particular problem in a homework assignment for that week, well, okay, I wouldn't do it. And if I didn't have time to deal with the chemistry topics that were exposed that week, I'd wait till the following week, and it's like a never-ending spiral.
Did you ever get help from your father with your physics homework?
On occasion, I would touch base with him and say, gee, I don't know how to approach this particular problem. And he would give me some good hints. Usually, I would get together with some of my fraternity brothers who were in the same class as me, or those who had been older than me, who had obviously gone through some of these required courses beforehand for some assistance.
Just as you were finishing your bachelor's degree, your father wrote a now quite famous paper on physical reviews, and this is the work I remember that he did on neutron diffraction and manganese oxide. And I associate it most closely with his Nobel Prize in physics that was awarded in 1994. At that time, right around when you're finishing up your bachelor's degree and thinking about graduate school, maybe, did you recognize the significance of that work? Or was it during grad school or later that you realized that your father was really doing something remarkable?
No, actually, while I was growing up, and also while I was in MIT, I mean, I really did not appreciate the significance of the work he had been doing up till then. It wasn't until I actually went to graduate school at the University of Illinois in Champaign-Urbana that the significance of some of that work, and specifically this work on the manganese oxide, became apparent. And in fact, most of the reason for the awarding of the Nobel Prize to my father was actually not for his foray into using neutrons for magnetic structure determination. It was for developing the whole science behind using neutron scattering as a structural tool for, in particular, very light elements like hydrogen and carbon and oxygen. Of course, these are the elements which make up life, and these are the elements where X-ray scattering, X-ray diffraction, was not sensitive for showing you the locations of them. And so neutron diffraction became a tool not just for the metallic elements, but also for probing biological things, and obviously magnetic things. Now, in fact, that work on the manganese oxide, he did before I was at MIT. He had done this work when he was actually still at Oak Ridge and developed the capability of using neutron scattering for probing magnetic structure. And of course, this is the very first tool that was available for telling people whether this particular atom has a magnetic spin that's of a certain magnitude and pointing in this particular direction. Up till then, there was no tool that was available for people to make such determinations. And so, in fact, this was really the beginning of magnetic structure in general. And that nickel or manganese oxide work you mentioned was work that showed that there was the existence of a ordered, long-range ordered magnetic state known as antiferromagnetism. It had been predicted by Louis Néel a number of years before, but there'd been no proof to show this. And with his manganese oxide work, they were able to show that at low temperatures, there were additional Bragg scattering peaks, which came about because you had a second lattice, a sublattice, that had magnetic moments ordered in the opposite direction from those which are apparent at high temperature, where it's paramagnetic, not antiferromagnetic. But yeah, I did not recognize the significance of that work, any of his work in scattering, because my father was very good at not pushing science on me and my brothers, but he was always there to explain the science behind things and to get you to appreciate that there are reasons for things happening the way they happen. But he didn't push it on us, and so even when we would go and visit him at the reactor, the nuclear reactor, either at Oak Ridge or Brookhaven or MIT, he didn't show us, oh, gee, this equipment was used to do such and such, or this is a useful probe of such and such else. But so he was kind of laid back and stayed back in that regard. But I took a course at the University of Illinois in Champaign-Urbana, given by my thesis advisor, Paul Beck, there, on magnetism, because at that point I was studying magnetic properties of materials. And he taught this course, and one of the things he brought up was showing this manganese oxide work. And so I looked up the paper and read in more detail what it was all about, and began to recognize significance of some of his work.
Did you know of Paul Beck from your father, or how did you decide that the University of Illinois was the right thing for graduate school? I mean, was it right after undergraduate work, or did you take a...
Right, so I went there right after my undergraduate bachelor's degree. But during the summertime while I was an undergraduate at MIT, of course, the first summer I was spent in remedial training, of course, but actually not completely. So the second semester, the summer, I spent working for a couple professors in the mechanical engineering department, Egon Orawan and Ali Argon. Now, here again, I did not know the significance of these particular individuals, but both of them were phenomenal developers of the science of dislocations and strengthening of materials. And I didn't know anything about dislocations or anything at the beginning. And then but after that summer where I was working with them part-time on torsion experiments and stress-strain relationships, which I liked a lot. And of course, this is a fundamental of material science. But when I went to my third year during the summer at MIT, I got an internship working for Union-Carbide Corporation in a place in the sticks called Kokomo in Indiana. Now, it was exciting to me to go out away from the East Coast, with the exception that there was no more ocean to go swimming in. But I was enthusiastic to go and work for a company, a real company, to find out what working in this field really was like. And while I was working in this laboratory on nickel alloys, Hastelloys, looking at an overaging effect, basically, is what it turned out to be. And that was my summer job, to find out why these particular alloys they're making huge ingots of were not as strong as they should be. And I concluded it was because of overaging, the temperatures and times they were using. But Paul Beck was a consultant of them. And one day he was coming out to give a talk to people at Union-Carbide. So I went to his talk. Unfortunately, I overslept that morning. And so I got to his talk late. And so instead of going in the main doorway to the conference room, I kind of went in from a back doorway from the secretary's office. And as I opened the door, I almost knocked Paul Beck to the ground as I opened the door, because he was standing right by it. So it was a very inauspicious meeting of him, but I was talking to him afterwards, and he said, well, he knew my father, and he would be interested in my coming up and visiting and seeing what that place looked like that summer. So we made plans for me to do that, and I also then planned to went up to Northwestern University to talk to John Hilliard about the possibility of graduate school there. And so I ended up applying to both of those schools at the end of my senior year. And I was admitted to both of them, and I was about ready to go to Northwestern University when Illinois offered me a lot more money. So being bought, I decided to go to the University of Illinois in Champaign-Urbana instead. And but I was only there for one semester, and this is, of course, right in the middle of the Vietnam War period. And I got my draft notice saying report to a physical up in Chicago on this particular day in February of that year, 1969. And I figured I would get out of being drafted because of my eyesight being so bad. And in fact, they did measure it as being worse than they could measure. You know, it's over 600 plus, as I remember they said. And but they took me, so I left graduate school in February of '69, and then I came back to University of Illinois Champaign graduate school in 1971 September. After spending 2 years defending our country in Oklahoma. And you'll notice that I was very successful in what I did because nobody ever successfully invaded Oklahoma while I was there.
So your thesis work was on Mictomagnetism and iron aluminum alloys. Can you describe what Mictomagnetism is? Even magnetic materials people probably don't understand what Mictomagnetism is.
Well, it comes from the Greek word meaning mixed, micto, as I'm sure you know quite well, being married to a Greek lady. At any rate, it was a term coined by my thesis advisor, Paul Beck, and it described the magnetic state of some particular materials, iron aluminum turning out to be one of them, where in a certain temperature range, its magnetic character looked like it was a kind of a combination of antiferromagnetic interactions working on the magnetic spins, as well as ferromagnetic interactions working on those spins. And it occurred in materials where the magnetic spins in that material were grouped together into clusters. So it was actually a clustered magnetic state, and the interactions between the spins in these clusters and the surrounding magnetic spins that were not in those clusters could be described by particular conformations of interactions, some of which are positive, in other words, ferromagnetic, or negative, or antiferromagnetic. And so Paul Beck coined this term Mictomagnetism, but it describes basically a cluster of magnetic spins which are acting cooperatively and interacting with the sea of other spins around them, as well as other magnetic clusters. And as a consequence, you get very characteristic magnetic hysteresis loops when you cool them down from a high temperature to the lower temperature. Typically, this magnetic state exists at lower temperatures than room temperature, and you would need to cool them down in a magnetic field in some particular direction. And so you get this, the signature of it is this magnetic anisotropy, where the hysteresis loop would be displaced from the origin along the field axis. But in the iron aluminum system, it was particularly interesting in the sense that in a previous graduate student of Paul Beck's, Hiroaki Okamoto, had measured one of these alloys from room temperature on down, and he found this data point that was outside of this normal systematics that you would expect. But Okamoto did not have that many data points in this temperature region. So Paul Beck suspected it was a real data point, and he wanted to explore that, suggested we explore that. And so I was quite interested in trying to do that. And it turns out that it was a real data point. And if you looked at the systematics with much, much more detail, it was quite unusual. And in fact, what we found in this particular system is that the material changed from ferromagnetic or long-range order to this clustered magnetic state, or perhaps more people called it not Mictomagnetic, but spin glass magnetic state at low temperatures, or paramagnetic at lower temperatures. So this is very unusual, of course. All ferromagnets become paramagnetic as you go up in temperature. Here was this material which went paramagnetic from ferromagnetic state as you cooled it below room temperature. So we coined this term, this inverse Curie temperature in this one particular alloy. I think it had 29.5% aluminum in iron. So it's basically iron in a very small amount of aluminum in it. And we basically one of the things that Paul Beck stressed was for all of his graduate students to build a special apparatus, and this had the dual purpose of, first of all, training the student in designing, and then having constructed some particular apparatus equipment. And secondly, then the laboratory in general had another tool they could use to explore other materials. And so the device that I was then charged to construct was some way to show that, in fact, this material, this iron aluminum alloy, was paramagnetic in this lower temperature region. And one way you could do that is to see if there's any remaining magnetic moment on that material after no field applied at low temperature. So I built this apparatus which would rotate quickly the sample at any temperature, and then you would have a coil around that sample. So as it rotated, it would induce a potential and thereby current in that coil, and you could deduce whether there was a remaining dipole moment on the sample, and that would tell you whether it was paramagnetic, which would have no dipole moment remaining, or ferromagnetic still, but you just couldn't measure it, which would have a little dipole moment, and you would pick up that induced potential. And so that was the device I constructed, and sure enough, showed that at room temperature, you got a nice big pickup in that coil, and at low temperature, there was none.
How did you make your samples, Bob?
So this was another thing that Paul Beck really stressed with his students, is to understand well the character of the material you're making your measurements on. And so he was a metallurgist from the very beginning, and he stressed that the metallurgy of the materials. And so we made these materials from arc melting iron and aluminum alloy metals, and then we would cold work it after quenching the material. And the cold work builds dislocation into the material, which then causes dendrites, which are formed in the solidification process, to break up and get moved all around. And then we would put it in under a vacuum enclosure in a sealed in quartz capsules and wrapped in tantalum foil to keep them from oxidizing, and then heated up to very high temperature. And then when we'd quench them and make certain that we quenched them very quickly into an icy brine solution and smashing these capsules as they got into the solution. So it would quench very quickly, thereby not changing the structure of the material from the high temperature to low temperature. And then we would cut out pieces, and we would use a grinder, a belt grinder with a little copper elbow upside down just over that paper on the belt sander, and with emery paper inside that little elbow, and these little cubes would then go bouncing all over the place and getting ground by the sander and the emery paper inside to form spheres. And you want a sphere so that you did not have any shape anisotropy to your measurements that you subsequently make on the magnetic property of the material.
So the treatment was for both microstructure and for crystal structure, getting everything so that you'd have these cluster formations that you need for the interesting magnetic properties. Was it for both of those things?
Exactly. And so we would conduct X-ray diffraction measurements on all the samples. We would measure. We would send it out for analysis of gaseous contents. We would do microstructure sectioning and observe it under a microscope and to get microstructures of these materials. So indeed, we would do a lot of work, or I did a lot of work during this thesis to probe the metallurgy of the material in addition to the magnetic measurements. And then we did a lot of, we wrote lots of programs for computers. Now, this was the beginning of computers, of course, and I would take this set of cards, so you punch out cards those days, and I would physically take these up the street to the computational center and put them in, and it would run a program I had designed and written for it. And it was very cumbersome. It was wonderful when I was a graduate student that we got this wonderful calculator made by Wang Corporation, where we didn't actually have to go up the street to the computer. It was basically a micro computer that the department had gotten and that we could use to do some fitting. So we wrote programs to try to fit our data to Brillouin functions and all sorts of things. So those were the early days of computation.
After graduate school, I know you went to Caltech for a postdoc. Did you go directly to Caltech?
So I did. I went directly to Caltech from Illinois, and the reason I did that was I went to work as a postdoc for a fellow named Paul Douay. Now, Paul Douay was essentially the father of rapid solidification, or metals which were not crystalline, that they were non-crystalline, they were amorphous materials. People didn't think that was possible until he showed this a number of years before I got there, and I have then explored that quite a bit. And my interest was, since I found that in the iron aluminum alloys that its magnetic character, including this reverse Curie temperature phenomenon I mentioned we found, was dictated by crystal structure. you could take the iron aluminum alloys in the composition range I was working in, and you could order them into the cesium chloride FeAl structure for the same composition, or you could order it at a different temperature range into what is called the DO3 or Fe3Al structure. Without changing composition, you could have it in those two different orderings. And some of my thesis work was examining how that changed the magnetic character of it. Or you could take this material in the cesium chloride structure and you could disorder it to the point where it was not the cesium chloride, but it was basically body-centered cubic structure. And so I thought, going out to Caltech and working with Paul Douay, I could work on iron aluminum alloys where we made them amorphous, to show my naivety. Okay, if we made them amorphous, then we eliminate a lot of this structural connectivity to the magnetic character, and this would be it would educate me quite a bit. At the same time as educate me in this whole new class of materials, which was really a big advent in material science in those days. This was a completely new class of materials, these metallic glasses that you could form. And so that's why I went out there. And I quickly realized that one of the big areas that where there was a lack of information was the heat capacities of these materials. And so I embarked on a project to build a probe that would enable me to measure heat capacities. And so that's basically what I did for the 2 to 3 years there. So most of the time was built constructing this apparatus, and only in the last month or two was I able to actually make measurements on these materials. But in the interim time, I learned a lot about metallic glasses. And I also came into contact with a fellow who's become very well known in that area, Bill Johnson, William L. Johnson, who came there as a young professor at exactly the same time I came there as a postdoc. And so we got to know each other quite well. And I made a trade with him. I told him I would teach him nucleation theory, which of course all good material scientists are taught in college. And in trade, he would teach me electron screening in a lattice. As an electron goes through a lattice of material, how it gets screened by positive ions in certain locations. So we each taught the other this other topic. And of course, you can see what was much, much more important was his knowing and learning about nucleation theory than my learning about electron screening. I had a good time there. And one of the things that I set out to measure was to look for an anomalous linear contribution to the heat capacity when you made the material amorphous. And I did this by making a series of metallic glass superconductors. Of course, superconductors, when it's superconducting, there is no electronic contribution or a linear contribution to heat capacity. And this is what I set out to do. And in fact, right near the end of my 3 years at Caltech, I had these measurements in hand, and sure enough, there was a slight linear contribution, but very, very small. And unfortunately, there was a group at Bell Labs which had come out using zirconium palladium materials and showed exactly the same thing about 6 months to a year before me. And as a consequence, I never published this data. I probably should go back and find it again and at least put it in the literature. But it was a little disappointing. Well, as both disappointing as well as exciting to measure this sort of thing, and in fact to be able to measure heat capacities on very, very small samples, which is what all we had to deal with by splat quenching, we would make these materials amorphous.
I was just going to ask how you made those materials. The rapid solidification was still pretty new, and Douay had his way of doing it, but there were other ways, right?
Right. So the way that Paul Douay found most, I wouldn't say effective, but perhaps give you a little bit more sample to work with. His original thing was to shoot a liquid out of a quartz tube with a high pressure jet onto a slanted piece of copper. And as that liquid hit that copper at an angle, it spread out and it got quenched quickly by the high heat capacity of the copper sucking the heat out of that liquid. Well, you end up with a very irregular material, mostly powders, and not a lot of material to work with. Whereas what he devised later was to slightly pressurize this quartz tube from the top, where you would liquefy your alloy inside it with a induction heating coil, and then slightly the pressure so it would drop out of that tube, but at a slow rate, and it would trip a little light sensor, and it would, which controlled a piston and anvil sitting on the side, would come smashing together, and hopefully you would catch that liquid droplet in the middle. And in fact, it works nicely, but you miss hitting that liquid droplet most times, or you'd hit it on the edge, or your plates would not be parallel, they'll be at an angle, and so it would quench that droplet at different rates through it. But you would get after doing this, I don't know, 50, 60 times, you would hit it maybe 4 or 5 times nicely, and you would get some sample, but not a lot.
But that was the way that you did your experiments for the heat capacity, right?
Correct. So I would make samples this way for doing the heat capacity.
You end your postdoc at Caltech. Did you go directly to NIST from there, or did you have some stops along the way?
So I took basically a 2-week vacation traveling across the country in a Volkswagen squareback car with, now I had 2 children, the oldest being 4 or 5 and the youngest being 2 at this point. So with our worldly goods in this Volkswagen squareback, and so we went up to Yosemite Park, and then several national parks as we traveled our way east, and just one step ahead of a big snowstorm which was coming. And so we had some motivation to keep on moving, but we spent basically 2 weeks traveling to go to the East Coast from Pasadena, California to Maryland, and where I had accepted this position as a postdoc at what was then called the National Bureau of Standards, or NBS. And in fact, if you hear me switching from NBS to its later name, which they changed the name in, I think, 1988 to 1997, I think it was, to the National Institute of Standards and Technology, or NIST. If I changed from one to the other, you'll pardon me. But yes, so I took this postdoctoral position at NBS, and my job was basically to set up the capability there of doing rapid solidification. This, as I say, this was a whole new area of material science, and so it's quite wide open in terms of what these sort of amorphous structures, what sort of properties that these amorphous structures resulted in different systems. But also at the same time, there was a big activity, again, led primarily by NBS, but jointly with the American Society of Metals for improving on and measuring and determining the binary phase diagrams of all these different elements. The big books at that time, Hansen's book, and then Elliott's and Shunk's compendiums to add to them. Most of the phase diagrams had dashed lines indicating that's what it's thought to be, but no, there have been no measurements or definitive determinations. And so they wanted to redo all these systems, all the binary systems and some of the ternary systems. So I kind of joined that effort at the same time at NBS as setting up the capabilities to do rapid solidification.
So when was this, Bob? About what was this the end of the 70s or the beginning of the 80s or?
Yes, it was. I arrived at NBS in November of 1979, and so that's essentially beginning of 1980. I began all this work in those two different areas. And so due to my experience of not getting very much sample by splat quenching materials, as I described earlier, I had looked around and decided a much more productive method for doing this rapid cooling of a liquid to the solid state would be by a technique called melt spinning. And here you have a very fast rotating, generally copper, but it could be other materials depending upon what alloys you're trying to rapidly quench. And you spit out from a tube an alloy that you have melted in an induction coil and pressurize it briefly so it shoots out this liquid from a hole in the bottom of that onto this fast rotating wheel. And you could, in the best cases, you would get these ribbons of material. And you get miles of ribbon for the small amount of liquid that you are injecting down, because the thickness of this ribbon would be in the mils range. And so I decided that was a much more productive way to do it. And so I set about constructing such a thing. And it also become important, I realized when I was at Caltech working with Paul Douay, that there are many alloys which, like titanium alloys in particular, but not just them, but which will oxidize very quickly when you heat them up to the temperatures that they have to go to melt. And that oxidation or nitriding from the nitrogen in the atmosphere will change the system significantly. So the system I went to construct at NBS for doing this melt spinning, I was positive I had to do it under vacuum, or at least in a system which could be evacuated from all the air in it, and then some inert gas reintroduced to it. And so that was the design I used, and we came up using a big bell jar initially, and with the top cut off, and then we put a big seal on the top and a steel plate. We used a big plexiglass plate on top that we then had the feed through for our little quartz tube sticking into it, and the induction heater inside the chamber. And so that's the system that I designed. And one of the first things that we tried melt spinning was for a guest scientist who had come to NBS at that time named Danny Schechtman. And he was interested in doing some rapid solidification of aluminum alloys. And one of them was an aluminum manganese alloy. So these are primarily aluminum with small amounts of manganese or other elements added to it to melt spin. And so a technician in this laboratory that I had this melt spinner constructed then did this for Danny. And Danny, being a wonderful electron microscopist, took these flakes that came out in flakes rather than ribbons, and took some of these flakes and looked at them under the electron microscope and found this unusual five-fold symmetry to it. And of course, that took a whole life of its own, these so-called quasi-crystals that were formed in this material. To show how smart I was, I decided this was not something I wanted to get involved in, even though I could see how exciting this was, since it went completely against all my training at MIT on what sort of symmetries are possible in crystals. They had to fill space, and therefore five-fold symmetry is completely forbidden. But I had another focus of looking at probing these metallic glasses, and so I kind of stayed out of that arena pretty much. And I don't know if that was good or bad, you know. At any rate, I focused on other things.
Well, he did get very famous. Of course,
Danny Schechter won the Nobel Prize.
I know. So famous or not, he did win the Nobel Prize. What was your activity with the titanium alloys? You described a little bit about this. This seems like a pretty practical thing to do, not related to melt spinning per se, I think.
Right. So this was in that second project or focus of at NBS at the time of the phase diagram clarification. And one of the a big industrially important system where there were at the I don't know, 5 or 6 conceptually different diagrams for the phase equilibria between titanium and aluminum at the titanium end of that binary system. So it's a binary system. The useful alloys tended to be quaternary and quinary type alloys with other elements like niobium and molybdenum and other things added to it. But the basics in small amounts, but the basic system was titanium aluminum with small amounts of aluminum. And as I say, this was like a lot of other systems where there were lots of dashed lines for this. And the big uncertainty was it's at high temperature, it was well known that the titanium aluminum system formed a complete solid solution of aluminum and titanium, forming a nice body-centered cubic structure. At low temperatures, it was also well known that at the small aluminum contents, again, nice solid solution of aluminum and titanium, but now in a hexagonal close-packed structure. This was called the alpha phase. That body-centered cubic phase at high temperature is called the beta phase. But it also was found by people that at much higher aluminum contents, that is, contents still less than 50%, but greater than, say, 30% aluminum and titanium, then the material would form a ordered hexagonal structure called the alpha 2 structure, or Ti3Al, was the prototype of this. But how you went from the disordered alpha hexagonal phase at low aluminum contents to this ordered alpha 2 structure as you added aluminum was very debatable. And debatable in addition to whether there would certainly be a 2-phase field between each of these 2 single-phase fields of alpha and alpha 2, but whether that 2-phase alpha plus alpha 2 phase field actually went up to high enough temperature that it intersected the body-centered cubic structure. And most of the diagrams which people were concluding to work with showed this intersection. And so that was the part of what I set out to clarify. And indeed, what we found is that the miscibility gap between these two hexagonal phases, alpha and alpha 2 at low temperature, they came together at a high temperature to a single point, and that single point was not at a high enough temperature that it reached the alpha beta two-phase field. And so there basically is a miscibility gap rather than an intersection of forming a paratectoid reaction with the beta phase, as most of the diagrams show. And in addition, even at higher temperatures and aluminum contents, we showed that there was a eutectoid reaction between the alpha 2 phase and an even higher aluminum content single phase called the gamma phase, which is also very important, industrially important structure, because it goes to very high temperatures before it decomposes into some other multi-phase system. So that was basically what I did, and it was very, very good to have finally clarified that, since it has a profound impact on industrial alloys. The alpha 2 Ti3A phase is very brittle. The alpha phase is not brittle. But if you get an intersection of those phase fields with the beta phase, then on cooling from this multiple phase field of including beta, you get surface rupturing when you go from the cubic to the hexagonal phase, which then means lots and lots of dislocations are imposed in the material in particular facets, and that's also can be deleterious to the structural integrity of the alloy.
So this was more of a practical project for you. This was
correct.
Something that was industrially motivated than the other side. So you had two very different things that you were working on, something very fundamental on one side in looking at the rapid solidification, something far more practical on the other side.
Right. And one of the things that actually I learned in this whole project was how important if you're doing experimental work on clarifying or determining phase diagrams in a system, it's very important that you approach a particular temperature and composition from above, that is from high temperatures down, making alloys that you quench from a single phase field that's above a two-phase field boundary, and also from alloys that you've quenched down to very low temperature, and then you sequentially age it at higher and higher temperature till you come to that boundary. It's very important to do both and make certain that it converges. And the second thing is to make certain you do a series of compositions that are relatively closely spaced in order to determine definitively determine that boundary. And this is something that John Kahn, by the way, John Kahn, of course, an extremely well-known material scientist. He was also at NBS at the time, and his office was ended up only a few doors down from mine. The one thing he taught me at the very beginning was to do that. And that was really important because that helped us to define the phase boundary between a single phase and a two-phase region definitively. And we could, in addition, determine differences between coherent phase boundaries and incoherent phase boundaries. That is where one of the phases is crystallographically coherent with one of the other phases across that boundary. So
very, very interesting.